was determine how the brightness of X and Y are affected. So we did do this in class when switch S is closed. What is brightness connected to? Power. So if you're looking at this one, is there anything going through light bulb Z at the moment? No. The question asked about X and Y. So you were told that they are identical and the cells have no internal resistance. So what happens when this switch is closed is that this one is going to get current as well. So if this one got 2 ampere, how much will this one get?
When the switch is open or closed?
We're closing the switch now. So at the moment, this one gets, okay, so initially when the switch is open, this one gets 2 ampere, so that means this one gets 2 ampere, right? Okay, so that's a series circuit now. Why are you frowning?
Does current remain the same in a parallel?
No. But it isn't a parallel circuit at the moment. When the switch is open, okay, let's start again. The switch is open. So that means the current comes here, here, here. It can't go to the top. There, there. Series circuit. Happy with that part? So it's a series circuit, so the current is the same everywhere. So if you look at these two light bulbs, what can you say about their brightness? They're in series with each other, they split voltage equally, same. Okay, so they will be the same at the moment. Now they're saying determine how the brightness of X and Y will be affected when switch S is closed. Now if you think about voltage, now remember the voltage in this one, at the moment, let's say it's a 6-volt battery. How much energy will this one and this one get per coulomb? What would the voltage be? Kalindi? You're working it out in your head, I can see.
While it's in series like that, right?
So switch open. As it is like the blue circuit now, well, each of them will get 3 joules of energy because they said the cells have no internal resistance. So that means if the coulombs leave with 6 joules of energy, they're going to give 3 joules to this one, 3 joules to this one. So that means they get the same voltage, they get the same current. So what can we say about their brightness?
Same.
They are the same because remember brightness is power. So if you look at the power equation, that power is equal to voltage times current, now answering this person's question, then you could say they get the same voltage and the same current, so therefore they must have the same power. If they were not the same resistance, then it would not be the same. So it only will work if they were identical. Now we're closing the current, the circuit here. So if we're closing it, now is the current going to go up? The total current, this current here, is it going to go up or down? We're opening another door. Up, because if we open another door, we're making it easier for the current to flow. So that means the current is going to go up. So immediately for this one, what can you say is going to happen to it? This one here. It's not going to get 2 ampere anymore. How much current? Okay, so if this one could take 2 amperes, how much can this one take? Also 2 amperes. So the current is going to go up to 4 ampere in an ideal world if there's no internal resistances. So that means that this current will go up and they still have 6 volts of energy to share. So this one is still going to get the same energy, but now so this one gets higher voltage, higher current, so this one will go brighter. So do you all understand that X will be brighter? Okay. Now for these two here, is the resistance here lower than what it was or higher than what it was? Lower than what it was, you know.
Switch open or closed?
Closed now.
Yeah, the resistance will be lower.
Yes, good. So the resistance is going to be lower. So that means here, am I going to use the same amount of energy here than what I'm using here? Or less?
It should be less.
Less, because it's easier to go through it. If it's easier to go through it, the resistance will be less, so the voltage will be less. So that means these two are both going to be dimmer now. With me? Because they're going to get less voltage, but they're still getting the same current. So if the voltage decreases, but the current remains constant, remember I said this to you guys when we started this. You can only use direct proportions if the other thing stays constant. So you can only say that the power will go down if the voltage goes down, if and only if the current stays constant. Remember that. That's very important. So that means you could have used the equation P equals V times I to explain it. You could have also explained it using the P equals I squared R equation, because I is constant, so that therefore, as the resistance goes down, which is true for a parallel connection, the power must go down. But if and only if the current remains constant. And then it says how the voltages change. We already actually spoke about that, because the voltage across here is going to be smaller because the resistance is lower. So now for ratios, if you are thinking about this circuit, let's just do it for this circuit. It's a similar one than what you had in the exam last year. So if we're looking at the ratio now, if this one gets so the current here is 1 to 1 originally. The voltage is also 1 to 1. So let's use another color. So the voltage is also 1 to 1. Happy with that? Now if we close the switch, what is happening to the current here? In this part here. Is this one going to get more current or less current? The total one. What's going to happen to the total current? The current is going to go up. So the current is going to, in the new circuit, if it was 1 in the old circuit, it's now going to be 2. You understand that?
No.
So let's go old to new. You happy with that?
No.
So if the old current was, no, there's a big no. All right, so if the current, remember if you're using the 2. So if this one could take 2 ampere, the total current was 2. So the 2 in that original circuit. Now if I'm closing this and these 2 light bulbs are identical, so I'm opening those 2 doors and you guys must run out. They're the same size door. So is the one door going to take more than the other one? No. So that means if this one could take 2, this one will also take 2. So this total will not be 2 anymore. What will the total now be? 4. So it will double. From old to new, it will double. Happy with that? Yes. Yeah. But the total current is bigger because it's easier to go through the parallel. So the total current will get bigger because this resistance drops. The total resistance drops. Okay, you always need to think about that. So if it's easier for the electrons to flow, more of them will flow, so the current will go up. Okay. If you're thinking about energy, if you look at this parallel connection, what did you say? You guys said that it's easier, right? So the resistance goes down. So am I going to use as much energy to pass through here than I am to pass through there? I'm going to use less energy here. Happy with that one? So if I go old to new, so this is current. So if I go old to new for voltage, then that means for the parallel connection now, then, so if we're looking, let's say at this light, for this light bulb Y. So if the voltage was 1, the voltage is now going to be half of what it was. You happy with that? So it just depends where they asked you for the ratios. Just think about it logically. Is it easier? Is it harder? Do I use more energy? Energy is always what? Joules per coulomb. So it's actually voltage. Voltage is energy. Current is particles running. If it's easier, there's more. Voltage is energy. If it's easier, there's less. Happy? Okay. Let's look at the next one. She also said for this one.
For our assignment, we're going to be ratios.
There might be.
Oh, no, man.
Oh, wait,
What color method that you were showing us the other time?
the voltage thingy.
Yeah.
Yeah? Do you like it? But do you want me to show it to you? Is that what you're asking? Okay, for that color method, it's for voltage only. So you draw a line. So every time the voltage changes, you change color. So if you're looking here, here goes, this is, think about the electrons. The electrons leave with how much energy? Did they tell us? Let's say it's a 6 volt. This time they say the cells cannot be ignored. So let's say they do, the EMF of the cell is whatever, 10 volts, but they leave the internal voltage, they still 1. So the electrons leave here with 9 volts, 9 joules of energy. So those electrons leave with 9 joules. How much energy do they have there? And now? And now? And now? And now? And now? 9. So keep 9. Okay? So when they get here, does the voltage change? No, it's still 9, 9, 9. The electrons that went here, do they still have 9? Yeah, still 9, 9, 9. They haven't given off any energy. Then when they get to this light bulb, is this light bulb going to steal some of their energy?
Yes.
Yeah, the light bulb steals energy, so it does. So when it comes out, does it still have 9? No, so you use a different color. These two light bulbs are the same. So will this light bulb steal the same amount of energy as that light bulb? Yes, so when it comes out, it's also going to be red. When they get here, so let's say these light bulbs stole 3. How much do they have now?
6.
And now?
6.
And now? And now? And now? No. And then they still have to, I couldn't make it 6. I'll have to make it less than that. But anyway, you get the idea. Then when they pass through the cell, do they lose energy?
No.
They gain energy, but is it the same as what it was here?
No.
No, because the battery also ate some of the energy. Please remember that. So now if you connect a voltmeter, that's the shortcut. If you connect the voltmeter anywhere between the same colors, so this between red and blue, this voltage will be the same as this voltage between red and blue, will be the same as this voltage between red and blue, will be the same as this voltage between red and blue. So whenever it's red and blue, the voltage will be the same.
So it's 10 in this case.
No, it's 9. Because the battery stole 1.
What's the 10 volt for EMF?
Because this question said you cannot ignore the internal. So that's actually the difference between question 8 and 9. Question 8, there was no internal resistance. So the battery is not stealing any energy. For question 9, there is now internal resistance. So the battery is stealing some energy. So it tells you, let me just make it very big. Throw those away. Okay, so it tells you that the circuit, the resistance of the cells cannot be ignored. And I'm very clear, or I think I'm very clear about it in the test. Every time at the top of the question, we tell you internal resistance are negligible, or you can ignore it, or you can't ignore it. Please read it. Make sure you know what you're doing. In this one, you cannot ignore it. The voltmeter has a high internal resistance. Okay, so that's just stuff that we have to tell you. We don't have to tell you, because you should know that a voltmeter has a high resistance by now in matric. Okay, when switch S is closed, how is the brightness of globe Y affected? So it's the same thing. So here we go. Electrons leave. They get here, same energy here, lose energy there. Light bulbs, again, exactly the same. So they're asking you, when the switch is closed, so now we're closing the switch, so think about open first. Open, it's a series circuit, remember? So that means if 2 ampere, I'm going to just use the same values. If 2 ampere could go there, how many amperes could go there? 2. So in the beginning, it got a current of 2 ampere. When you close the switch, it still gets a current of 2 ampere. Happy with that? But this time, the internal resistance cannot be ignored. So that means if the EMF is 10, again, 10 will not go out. So 9 volts will come out, or 9 joules per coulomb. Here goes 9 joules per coulomb. They're giving it off only to that one. Now, if I close the circuit, the electrons that go there and the electrons that go there will still have 9. So will they have the same voltage? Yes, and they will have the same current. But
Why?
Will they have the same current because the equal current?
They told you, actually we didn't tell you that the light bulbs are identical. I'm just assuming that they are identical.
They'll be equal, right?
Yeah.
What if they got them to be different?
Yes.
So So, ma'am, if you don't tell us anything, we can assume it's identical.
We should tell you. Yeah, we definitely should tell you. Okay, so where were I? So they're asking about the brightness. So if we're looking at the brightness of the light bulb when the switch is closed, what is happening to the resistance in that whole bit? The resistance is going to decrease. As soon as the resistance decreases, what is going to happen to the current? The current is going to increase. But what's going to happen to the voltage?
Same.
Say again? I heard it somewhere. Who said? Bloody masks. I can't see who talks. No.
Voltage.
If it's easier to pass through this bit. No? If it's easier to, the current increases. Yes, so the current increases. So what's going to happen to the brightness of the light bulb? It actually does get dimmer. Did you read it from your answer?
No, I don't have the answers now.
It does get dimmer, but why? No?
Does the voltage
But why does the voltage... So in the other one, the voltage didn't change. But in this one, the voltage does change. And remember, you're going to get a question like this, guys. I've done so many of these. If you think about it now, the current is going up, right? So that means I times little r. What happens to it? Little r is constant. It increases. So if the current goes up, it means that I times little r will go up. What is I times little r? Internal voltage. It's the energy that the battery eats. Now in this case, the battery ate 1 joule. Now the battery is going to eat more. The battery is going to eat 2 joules, for instance. So is this still going to be 9? No, so now these electrons only leave with 8. So are they going to give the same amount of energy to these light bulbs? No. So what's going to happen to the brightness? Decrease.